more like an amplifier.
Okay, so have the same.
Okay, thank you. So the topic of our project was optimizing the training time and inference performance of LLMs. And we executed the project in a Ferment team with myself, Robert, Szymon, and Mateusz over there. Well, there are many ways of optimizing LLM performance. It's a hot topic with LLMs popping up in every industry right now. And there are many methods of doing this, but our project focused on a specific one. To be more specific, our work was based on a paper from October 2023 by a team from IDEAS and CBR. The paper was called Mixture of Tokens, Efficient LLMs Through Cross-Example Aggregation. What the paper does is is an extension of expert choice mixture of experts through continuous token mixing for more stable training. And I will explain what all of those words mean. And the goal of our project was to create an implementation and share it with others so that they may more easily experiment with either this method or a similar one. So I will actually start not with mixture of tokens, the one method we used, but with mixture of expert, a more general approach. So let's say we have a large language model, some architecture, and we want to train it and we want to do it efficiently. We can focus on different parts of the model, but a large percentage of the parameters is dedicated to the NLP layers. On the right here, you can see a graph showing the distribution of the parameters between different layers of models at different sizes. And you can see that for a large GPT-3, the red part is the feed-forward one. The NLP layers take around 70% of the parameters. So if we can optimize the performance of training those, there will be some big gains. Can we use those parameters more efficiently? Well, there's an intuition that a lot of the computation that's happening within those layers is actually sparse. We only express it as a dense matrix multiplication because that's the way we can compute it efficiently on GPUs. The idea for the mixture of experts models is to replace this single MLP layer in each of the transformer blocks with some smaller MLPs and then a so-called router to direct the tokens to be processed by only part of the network. The remainder of the transformer architecture remains unchanged. We only change this single layer. For each token, we compute its affinity to each of the subnetworks. This is done by a separate small linear or a feed-forward network. Once we have those affinities, we can think of them of how well suited each of the experts is to processing that token. We call the subnetworks experts because we expect them to specialize in some meaningful way. Once we have those affinities, we compute a softmax over them so that for each token, we can choose which experts knows the most about it, will contribute the most knowledge once we pass the token through it. Once we have computed that softmax, we can choose the top K experts and only send the token to that part of the network, those top K experts most suited. And once we have computed those expert outputs, we can combine them and process the token further through the network as usual. What are the effects of applying this earlier method? Well, we use less compute for each token. Instead of a full width MLP, we can choose, for example, if we have 8 experts and send the token only to the top expert for each one, we use 8 times less compute. Well, actually what we want to do is usually we have a set compute budget and we want to build the best model within that budget. So what we do is we increase the total number of parameters. But each time we do a forward or backward pass on the network, we only use some of them for each token. We do this because bigger models reach lower perplexity, so gain better understanding of the language with a given compute budget. In practice, this can lead to savings of around 3 or 4 times. It is used widely in the industry, different versions of it. The one model that you may be familiar with is GPT-4. We don't know the architecture for sure, but it is widely assumed to be some version of a mixture of experts model. That was training, and once we do inference, for a given token, we only activate part of the network, so we also have gains there. Moreover, because the layer is split into different sublayers, if we are doing a training on a big cluster, we have a natural way of parallelizing this training. We can just allocate each machine one of the MLPs. Well, those were the benefits, but there are always some drawbacks. And for a mixture of experts, the drawbacks are that to achieve a given power of the model, a given understanding, the model will have more overall parameters. But remember, only some of them will be used for each example. We still need to load those parameters somewhere. So if you're limited in your VRAM on your GPUs, this may not be the best solution. And the third and the biggest drawback is stability. We'll cover it later. What are some other problems? What can go wrong here? Well, because we are choosing an expert for each token, and we're not enforcing it anyway right now, that all experts will get the same number of tokens. For example, it may emerge that one expert is well suited for all of the tokens, and what will then happen? All of the routing network will learn that, and it will direct all of the tokens to go to that specific expert. What happens then is we will have a bigger batch size for that given expert. And because our frameworks and our GPUs usually assume a constant shape of a given tensor, we usually have to create a bigger tensor just to cover that case. And if we get even more tokens routed, we just don't process them. It's not as big of a problem as it sounds, because transformers use a skip connection around those layers. So skipping an update in one block is not tragic, but it still hurts our performance. Moreover, if we have uneven batch sizes, uneven number of tokens for each expert, we have to wait with computing the next layers before we have to wait for all of the experts to finish computing before we can move on with the next layer. That can cause the computation to stall if one of the experts has a bigger batch size. Because we want constant shapes, we have to cap the capacity of each expert so that it can only process a maximum of some tokens. If the capacity is exceeded, we need to drop those tokens. Moreover, if some experts go unused and some other experts become too powerful, that part of the network will be dead. We will have unused parameters that we are loading and trying to train, but we're not properly using. That was the first problem, the uneven expert utilization. And the second problem is that we are taking a top K operation. Earlier, we computed the affinities and only routed to the top experts for each token. And taking that operation, well, top K is a discrete operation. It's not natively differentiable. We have a natural gradient estimator. We can just copy the gradient from the input to the output, but it's still not mathematically perfect. And it is also inherently unstable because small changes in the affinities can lead to the computation taking a whole different path. And that can lead to unstable training. There are different ways of combating each of these problems. There are some auxiliary losses, some extra regularization, but maybe we can tackle this through architecture choices. Let's focus on the first problem, the uneven expert utilization. There is a pre-existing version of mixture of experts which tackles this. We want to guarantee that each expert gets the same number of tokens. It gets used with the same frequency. Previously, we computed the affinities, and for each token, we sent it to the top experts for that token. But what if we didn't take the top k over experts, but instead, for each expert, we took it over tokens? Well, in that case, each expert will have the same k, so it will have the same number of tokens. If we choose, well, we can choose the average number of experts that will process each token to regulate the compute, such as earlier we chose that we sent each token to the top k experts, and now we can set the capacity of each expert to match the compute use in that one. Still, some tokens may not be in the top k for any of the experts, and they will get dropped. There's not really anything we can do about that here. Once we take the output of the experts, we combine them with a weighted sum. This is not really obvious that it's going to work, but we're actually doing that for the earlier versions of MOE, and it's kind of important that this works. This version outperforms the regular mixture of experts, and it was introduced by Google in their paper. But let's look at some extra problems that we introduced while solving our expert utilization problem. Well, I said earlier that for each expert we take the top k over tokens. We take the top k tokens. Well, let's think about the size of the batch that gets into the MLP. The dimensions are the regular batch size, but there's a second dimension of sequence length. If we just flatten that array and take the top k over, okay, let's go dimension by dimension. If we take a softmax across the sequence length, so we process each example independently, we actually break causality, because the affinity for a later token, once combined through softmax, can actually influence the routing of an earlier token. So we cannot do proper autoregressive decoding. On the other hand, if we take the softmax across examples, we will break the independence of examples in a batch. And if we take a softmax across both, we will break both. Let's focus on the other problem that we signaled earlier, that top k is discrete. And we're finally moving on to the model that we actually covered, which is the mixture of tokens. What if we didn't really choose the top k of the experts? Well, then we wouldn't have the stability problem, but we also wouldn't have the compute savings. We'll just have more MLPs where each of them gets used. So the idea in the mixture of tokens paper that we prepared an implementation for is that, well, if we're already combining the outputs of the different experts, maybe we can combine the tokens before we process them in each MLP. We calculate the affinities like we did for expert choice MOE, the last one that I talked about. We then group tokens. We can think of grouping as taking the softmax over either the sequence length or the batch dimension. And then the other part of the routing works like regular expert choice MOE. The difference is that we are not taking the top k, so we don't have the stability problems. Additionally, we will not be grouping over the whole batch dimension. We will be taking a subset of that and grouping within each subgroup. And because our compute reduction is actually determined by that group size, we can tune that group size, for example, to be equal to the expert size. So if we have 8 experts and combine 8 tokens into one before processing them, we get the same active parameters as for a regular dense model. Okay, so what are the results of doing so? Well, it of course depends on the hyperparameter choices. But what was reported in the paper was that if you split, if you create 512 experts inside each MLP layer, and you tune the size of each expert so that the combined MLP would be 32 times wider than the original model, and then you group 32 tokens before processing to get the same compute. Then you will actually train 4 times faster in terms of the steps taken and 3 times faster in terms of time. That slight difference is because, well, we are doing the routing and also we're doing more independent computations, so we lose some efficiency there. What was our main contribution here? Well, that paper was implemented in a research repository where it was intertwined with lots of other experiments. It was not easy to conduct your own experiments, and also there was no public checkpoint for you to try a mixture of tokens for yourself. Our goal was to make it easier for others to experiment, and where do people go to experiment with models? They go to Hugging Face transformers. We also saw it with the earlier project. So what we did was we extracted the code from the research repository, and we ported it to the Hugging Face library. People are familiar with that format, so that it is then easier for them to experiment. We also trained a checkpoint and shared it, and we prepared a pull request for the mixture of tokens code to be merged into the main library. Mixture of tokens that I talked about is a broadly applicable technique. You can modify any transformer architecture by just swapping out that MLP. For our implementation, we converted a GPT-2 model by swapping out the MLP. The implementation that we created is self-contained. You don't need to look at lots of files and track the inheritance to find out what's really happening. It's self-contained in just 2 files. That's actually the policy for Hugging Face transformers. If you want to experiment with a different model and see what results you get by applying this technique, you can just steal our MLP replacement and plug it into your own code, and you're all set. The pull request, for the pull request, we prepared full testing and documentation. That pull request is currently pending. Well, if the technique gets enough community interest, it may get merged into the main library. But you can actually already try it on your own without compiling the library.
Yeah, so we train our model on our local cluster on entropy. This was the smaller version of the model from the paper. It was like 500 million parameters, something like that.
337 million. Actually.
Yeah, and okay. And during training, it's seen about 1 billion tokens, and it was trained for like 24 hours or so. And yeah,
the expansion rate that we used was similar to the paper, yeah. So that this mixture of tokens this mixture of tokens model had like 32 times as many parameters as the dense model that we based it on. But remember, the active parameters are the same.
Yeah, and we shared our model on Hugging Face. The checkpoint is there, so you can try it yourself. Now it is used without the different Hugging Face sharing model technique. It's not already on the transformers library, but you can use the auto model from Hugging Face transformers.
And to be clear what that means, you don't have to like pull our code and do all of that. You can just open up Google Colab and just paste in those 4 lines, and you have a model all set. What merging the PR will change is you won't have to have this flag here to trust the remote code. And yes, this is not a live demo, but an example of how it actually works. And we asked our model if mixture of tokens is better than a dense model, and it replied, I am. So we can see that it is self-aware. Well, what are the caveats? Our model is only a text completion model. It has no instruction tuning, so don't really expect it to follow your commands like a chat model would do. Our model is relatively small, even though it has like 300 million parameters. Remember, only 1/32 of that actually gets used in each pass. There are also some caveats related to not our choices, but the choices related to the whole mixture of tokens technique. Unbatched inference is inefficient because we need to group those tokens to get the compute savings. If you're trying to just do inference on a single example, you're going to have to use a lot of padding, and you don't get those same compute savings there. And if you do batched inference, this isn't private. Well, remember that I earlier talked about if you take the softmax across the batch dimension, then one example in the batch can influence another. If you're trying to use it for a case where, for example, different examples in the batch can be conversations for different users, that's going to be a problem. That's actually a problem that you can correct. Some further research from the same group showed that you can create a regular token choice, so the first technique that I described, mixture of experts, from this model by just copying the weights that are shared between for the layers that are shared between the architectures, and just retraining the token choice routing from scratch. And that step takes like 10% of the compute budget that you use for the pre-training to recover the whole performance. So you can get the benefits of the stability of training with mixture of tokens and then still perform inference like a regular mixture of experts models. If you want to try our models, that is the handle for the Hugging Face hub. Thank you.